Disclaimer. This episode features characters with Scottish accents. It is not intended to mock or stereotype the Scottish accent or culture in any way. All portrayals are meant with respect and for entertainment purposes only.
Captain's log, stardate 1736. We are currently orbiting the mathematical anomaly known as region Tau, an uncharted sector where the laws of geometry have completely broken down. Our instruments no longer detect straight lines. Everything is squishy.
Captain, the coffee mugs have mutated. They've turned into donuts, sir. It's happening a third time.
That confirms it. We're definitely in a topological zone.
I.
It all began with 7 bridges and 1 mathematician. Can you cross each bridge exactly once? Euler solved it, not with a map or with our star charts, but with abstraction, focusing on connections and ignoring the distances. Since entering this region, we've observed one sided hallways, infinite loops in finite space, a Mobius cat we cannot pet from both sides at once. And we're likely to find a lot more of these anomalies. Ensign, you better keep an eye on that. Last thing we need is a sugar rush on board this ship.
I, Captain. One more donut mutiny and I'll start hiding the cream. I.
Hello, and welcome back to Solving for X. I'm your host, your co host, Ramit, here today with our other co host, Nuha.
Hi everyone. Today we're gonna talk about shapes.
More specifically, we are exploring topology, which is the study of the properties that remain unchanged through deformations like stretching or twisting. Tearing, however, is not allowed.
Which is why it's also called as rubber sheet geometry, since the objects can be stretched and contracted like rubber but cannot be broken.
One of the central ideas in topology is that spatial objects like circles and spheres can be treated as objects in their own right, and knowledge of objects is independent of how they are represented in space. Meaning, we care only about the essential structures of shapes, not the exact way they look or are drawn.
For example, in topology, a coffee mug and a donut are the same.
Whole.
Yes, a donut is considered the same type of object. Why? Because they both have one hole. You can imagine reshaping a mug into a donut by stretching the handle into a loop and morphing the rest of the mug into the torus shape without cutting or gluing anything.
This is the intrinsic property of homomorphism, where you can't tell the difference between breakfast and your dishware.
Let's look at some of the objects that fall under this topological shapes. First up is the famous Mobius strip, which is a surface with only one side and only one edge. You can make one yourself by taking a strip of paper, twisting it, and then taping the ends together.
What makes it so fascinating is its non orientable surface, where the concepts of left and right or inside and outside break down. On a Mobius strip, if you travel along the surface in a continuous loop, you'll return to your starting point flipped, like your mirror image. This means the surface doesn't have a consistent orientation, making it non orientable.
From a mathematical perspective, this feature of the strip makes it fundamentally different. No matter how much you twist or turn the strip, it will always remain non orientable, which means it's the property of orientability that remains unchanged. And any property that remains unchanged is called an invariant in topology.
Another classic shape is the torus, which looks like a donut. Topologically, it has one hole, and that single hole gives it its identity. Unlike a sphere, which has no holes, a torus can't be deformed into a sphere without tearing.
Speaking of the sphere, it's perhaps the simplest closed surface in topology. It's the surface of a ball and has no edges. Even though we know what a sphere looks like, even a lump of clay is considered the same thing because it has no boundaries or holes.
Next, we have Klein bottle, which is one of the most fascinating shapes in topology. Imagine a bottle where the neck curves around and connects back through the side, merging seamlessly with the inside. In our 3D world, the neck of the bottle needs to pass through itself. Back in a four-dimensional world, there's no self intersection involved.
Again, like our Mobius strip, this Klein bottle has a non orientable surface. But let's be clear, having that one invariant does not mean that the two shapes are similar. A Mobius strip has a boundary, while the Klein bottle is a closed surface and has no boundary, but it can be embedded in 3D space. It can be constructed by joining two Mobius strips along their edges, but this does not make the two topologically equivalent, which is the same thing.
Ugh, topology, topology, topology. Who's the darn fool that came up with it? Why would they invent such a thing? All assumptions and nonsense.
Well, topology is new. It emerged in the 18th and 19th centuries, but its roots go back even further. One
Oh,
of the earliest and famous problems that hinted at topological thinking was the seven bridges of Königsberg problem, solved by Leonard Euler in 1736. The city of Königsberg, which is now Kaliningrad, Russia, had seven bridges connecting different landmasses. The question was simple: can you walk through the city and cross each bridge exactly once?
whoa, well, I need a map.
It's not possible. Euler showed that it is impossible.
Of course, how can I forget topology is all about twists and turns and complexities and puzzles and whatnot?
More importantly, he solved it by focusing on connections, not distances. This marked a significant step from geometry to graph theory, which is the foundation of topology.
Hmm, yeah. Well, now it's time to shed some light on some quite interesting theories of topology. Two of the most famous ones are the Brouwer's fixed point theorem and the knot theory.
Sounds very topological.
To serve some math nerds listening, I'd like to begin with the Brouwer fixed point theorem states that any continuous function f sending a compact convex set onto itself contains at least one fixed point, that is a point fx equals x.
And this is exactly that fixed point where math gets boring.
Not until examples grace it. Consider a map of a country. If that map is placed anywhere in that country, there will always be a point in that map that represents that exact point in the country.
Kinda like an overlap of a unique point on the map exactly with that particular place in the country. In it?
In it?
Yeah, sure, why not?
Yes, but if it's still confusing enough, the next example would get you rushing to your kitchen. If you take a cup of coffee and slosh it around, then after the sloshing, there must be some point in the coffee which is in the exact spot that is that it was before you did the sloshing, though it might have moved around a bit in between.
Okay, you know what? I'll just get myself something.
I know it. The example has done its work successfully. Anyways, are we ready to untie some special knots? If possible, though.
Are you about to?
Yes, the knot theory has finally come into picture. It is a branch of mathematics that studies knots, but not like the ones you tie with rope and then untie. In knot theory, a knot is a closed loop. Imagine taking a piece of string, tying a knot in it, and then gluing the two ends together. So it forms a complete unbroken loop.
How I wondered why you said if possible, air quotes involved.
It pretty much answered now. Two questions rise, by the way. As I already hinted, the first one is whether a curve is truly knotted or can simply be untangled. That is, whether or not one can deform it in space into a standard unknotted curve like a circle.
Hmm. If a cup and a donut are one and the same thing in topology, then
Exactly. The second question is whether, more generally, any two given curves represent different knots, or are they really the same knot in the sense that one can be continuously deformed into the other?
anyways, how do we know about the complexity of any knot?
Right. For that, we have the crossing number. Picture the shadow of the knot under a light and count the number of times the projection crosses itself. noting at each crossing which direction goes over and which goes under.
So it can be defined as the minimum number of crossings in any possible projection of that knot, right?
Yes, and it is a fundamental characteristic used to classify and study knots.
What's the simplest possible knot in topology? Because I'm tired of
Well,
complex things.
yeah. Well, it is the trefoil knot or overhand knot, which has three such crossings. The order of this knot is therefore denoted as three. Even this simple knot has two configurations that cannot be deformed into each other, although they are mirror images.
So, how many max crossings can a knot have?
There are almost 10,000 distinct knots with 13 crossings and over a million with 16 crossings. By the way, that's the highest known by the end of the 20th century.
16? Good lord.
In topology, knots can be represented as diagrams called knot diagrams. Certain higher order knots can be resolved into combinations called products of lower order knots, just like a vector in physics. For example, the square knot and the granny knot, it's like a sixth order knot. They are both products of two trefoils that are of the same or opposite chirality or handedness.
Chirality! If you know, you know.
Why not?
And what if a knot cannot be resolved?
See, knots that cannot be so resolved are called prime, just like prime numbers in math. Don't have factors other than one and the number itself.
Makes sense.
Topology already has addressed a vast collection of problems and subfields with distinct stories, although it has been around for like a few centuries only.
Like patterns in palms and fingerprints. They have common features such as loops and trieridae. In 1965, Lionel Penrose, a British medical geneticist, pointed out that the fingerprints and palm prints obey a universal rule. Everybody born with five fingers always has four more trieridae than loops. By the way, trieridae are three lines which are coming together.
Interesting. Okay, we also have the hairy ball theorem, which states that for a ball or sphere, rather, covered in hair, it is impossible to comb all the hair first, flat. There must be at least one place where the hair sticks straight up.
It can also be related to the Earth, which is roughly a sphere. The theorem implies that there's always at least one point on Earth where the wind isn't blowing in a horizontal direction, where the wind is vertical.
Hmm. Another process in topology is sphere eversion. It is the process of turning a sphere inside out, but without tearing, cutting, or creating sharp creases. So, like you're allowed to let the surface pass through itself, like, transparent ghosts crossing each other.
Ooh.
But you can't poke a hole or make a corner.
Think of a rubber ball which is soft and flexible. Now you want to turn it inside out. So that what was outside becomes inside, and vice versa. In normal life, we'd cut it, flip it, and sew it back. But in topology, it's all magic.
Then there's the Poincare conjecture. It is now a theorem in topology about the characteristics of a three dimensional sphere. In simpler terms, it states that if a three dimensional shape has no holes and boundaries, then it is topologically equivalent to a three dimensional sphere because it can be transformed into one, and it is often generalized for higher dimensions only.
Topology isn't just about shapes and patterns or donuts and spheres. It can be extended to a more complex and vast field concerning the cosmos called cosmic topology, where it is being used to determine the shape of our universe.
We might imagine the universe as infinite, stretching out in every direction forever. But what if that's not the case? What if the universe is finite, yet unbounded like a sphere? What is it?
A flat surface is one where the rules of Euclidean geometry apply. That means parallel lines never meet and the angles in a triangle always add up to 180 degrees. If the universe is flat, it suggests a certain kind of infinite extension, where space isn't curved in any direction.
But two other shapes of the universe are possible, open and closed. An open universe has a negative curvature, just like a saddle shape where lines that start parallel may diverge. A closed universe has positive curvature, like the surface of a sphere. It's like a saddle shape where lines that start parallel may diverge. A closed universe has positive curvature, on the other hand, just like the surface of a sphere. In that case, space curves back on itself, and traveling far enough in one direction might bring you back to where you started.
Scientists look at large scale observational data, especially the cosmic microwave background. It's a faint radiation left over from the Big Bang, continuing clues about the shape of our universe.
Yes, measurements from Planck satellite show that universe is extremely close to flat. This doesn't mean it's exactly flat, but it strongly leans in that direction, at least within the limits of our observations.
But why does it all matter? It is so because it is an ultimate observation that decides the fate of our universe. If space is flat and infinite, it could mean that the universe will expand forever.
And if it's closed, expansion could someday reverse. And if it's open, the cosmos might grow increasingly cold and empty. All this also influences how we think about time, gravity, and even the possibility of multiverses.
Alright, topology might be sounding a bit boring for you arithmophobic people out there, but it doesn't have to be just squiggles and equations on a chalkboard. It can show up in some unexpected places, like say in your cells. Do you want to guess where exactly?
Mitochondria, ribosomes, that weird gel stuff, the reticulum thingy, I
Okay.
guess.
Nucleus, yes. Mitochondria, kind of. Weird gel stuff. Cytoplasm, okay. Points for
What the hell?
enthusiasm.
I am just trying to name every term I remember from 10th grade biology. It's going great, clearly.
Gold star for effort. But
Thank you.
seriously, topology shows up in DNA. During replication and recombination, which is when DNA is duplicated and exchanged, it can form knots and links and become tangled like those wired headphones. Enzymes called topoisomerase do literal topological surgery by cutting and twisting the strands of DNA to ensure proper function and maintenance of genome stability.
Hairstylists for DNA? Cool, I guess.
Sometimes DNA also undergoes supercoiling, which occurs when the double helix twists upon itself. It can be positive or negative, and it affects the accessibility of DNA for processes like transcription, replication, and repair.
Where's the math in this exactly?
Okay, so there are three key invariants: linking number, twist, and write, which are connected by the equation linking number is equal to twist plus write. This basically says that the total number of times the two DNA strands wrap around each other is equal to how much they twist plus how much the entire molecule wriggles or writhes in space.
Oh, so you can't change the linking number without cutting the DNA? That's what makes it topological.
Now, proteins.
Ah, yes, your favorites. These are linear polymers or chains of amino acids which are responsible for most cellular functions. Unlike normal molecules, these divas have different levels of structures. The chain forms helices and sheets called secondary structures, and these fold up into hollow woolly and tertiary structures, which in turn combine to form quaternary structures.
Wow, I guess I do talk about them a lot.
Yeah, think?
Never mind. In the context of topology, some proteins have knotted structures you can't untangle without breaking the chain. And topology helps us study which folds are possible, which ones are stable, and which ones are basically the molecular version of a bad hair day.
Hmm. And a bad hair day is a misfolding of the protein, which can lead to aggregation and is implicated in diseases like Alzheimer's, Parkinson's, and prion disorders.
If you model the protein as a one dimensional curve in three dimensional space, you can use knot theory to analyze it. And just like in DNA, you can use topological invariants to study these folds. like width, chirality, and linking number, especially for proteins that wrap around other molecules.
Understanding protein topology is crucial not only for basic biology, but also for biotechnology, where engineered proteins with specific topologies are used for enhanced stability or novel functions.
Biotech and pharma researchers use topological models to predict protein behavior, design drugs, and even create synthetic proteins that fold in specific ways. Shout out to Dr. David Baker for designing AlphaFold and stuff like that.
Okay. Okay, enough of biology. Let's talk about something fun.
Hey, biology is fun. But okay. Like what? Topology in pop culture?
Okay, very well then.
Our listeners may be wonderstruck by now, but yes, you can even find topology in sci fi movies and pop culture, like the classic wormhole.
Yes, so in like science fiction, wormholes are imagined as shortcuts or tunnels through the fabric of space and time that instantly connect two distinct points in the universe.
Often, wormholes serve as gateways to alternate universes or parallel timelines, in stories, of course. The concept of warp drive, which allows starships to travel faster than light, implicitly relies on topological ideas.
Topologically, this is about non trivial connectivity, meaning points that seem far apart can actually be directly linked. It suggests that ability to fold or warp space time, creating shortcuts between distant points. This warping implies a non Euclidean geometry where distances can be drastically altered.
A tesseract is often portrayed as a four-dimensional cube or a higher dimensional space that can fold or manipulate reality beyond our 3D understanding.
Unlike a regular cube, which has length, width, and height, a tesseract extends into a fourth spatial dimension, allowing for impossible geometries and shortcuts through space or time.
Obviously, the real physics behind wormholes, warp drives, and tesseracts is still theoretical, but these ideas stretch our imagination and show how topology can help us think beyond the ordinary.
All right, now it's time for a quick activity break. Because sometimes, in order to understand topology, we need to mess with reality itself.
All you need is a piece of paper, some tape, maybe a pen, and glitter.
You don't need glitter.
People need glitter.
Okay, whatever. First, cut a long strip of paper, maybe an inch wide and 10-inch long. Twist one of the ends of the strip and then tape them together.
Voila, you've made a Mobius strip. Now take your pen or pencil and try drawing a line down the middle all the way around.
You'll notice that you won't have to lift your pen, meaning it has only one side. We talked about this, people. Remember?
If you want, you could also cut it down the middle and you'll end up with a larger loop. Huh, I guess we did not need glitter.
Yes, exactly. Give it a try and send us a picture if you can at solvingfor.x.official@gmail.com.
So, with this, we are at the end of today's episode titled The Whole Truth About Topology. In this episode, oh, sorry,
Thank you. In this episode, we have talked about shapes, knots, wormholes, Mobius strips, and a lot more.
we have, in essence, tried to bring a very unfamiliar and abstract topic to show how mathematics doesn't need to be boring or intimidating.
Once you start seeing the hidden patterns and the strange shapes around us and how everything connects, mathematics can become pretty exciting.
Thank you for tuning in, and we'll see you next time, only on Spotify and YouTube.
This is Ramit.
And this is Nuha, signing off.